IH bar minus IH bar. Yeah, that's it. Minus IH bar. Right. So now you got a minus minus, so hence plus. So just live with IH and the LZ here. So you've got this, and this here is not 0. Okay. Therefore, the commutator is non-zero, and therefore the x component of the angular momentum operator L hat, so Lx hat and Ly hat, if you put them into the commutator, the answer is this, non-zero. Therefore, Lx hat and Ly hat are incompatible. Okay? Therefore, you cannot measure both of them to infinite accuracy simultaneously. Okay? So you get this. Now, you can go through the same calculations, again, homework, for Ly LZ, and you'll get the answer IH bar Lx, and similarly for LZ Lx. In fact, there are, what, 6? So 3p2 in terms of permutations, combinations. There are 6 possible commutators you can make, and if you have A hat, B hat, the commutator would be minus B hat, A hat. So you only have to do 3. And the other 3 you know just by changing the sign. Okay, so for all three possible pairs, distinct pairs, all of them are non-zero. The commutators are non-zero. So any pair of those 3 components, Lx, Ly, Lz, they are all incompatible. Okay, any pair is incompatible. All right. Okay, so that means that you can only measure one of them with accuracy. So remember, if you measure one, you'll get one of the eigenfunctions, and therefore if you measure it again and again and again, you keep getting the same value, because the wave function, the general wave function, before the first measurement, will collapse into one of the eigenstates, right, with a given eigenvalue, and if you measure it again and again and again, you'll keep getting the same eigenvalue, the same measured quantity, the same value. Right? So that means you can only know the angular momentum value, the eigenvalue, the actual measured value of the angular momentum. You only know one of in one component, either the x direction or y direction or z direction. Okay, and the other two you cannot know with infinite accuracy. Once you've measured, for example, along the x-axis. Therefore, you don't know with accuracy what the angular momentum is along the y direction or the z direction. Okay. All right. But interestingly, if we can go back to here, let's call it the total angular momentum operator. Okay, squared. You again do it for homework. Find the commutator for L squared Lx, and you'll find that it does commute. It's 0. And similarly for L squared Ly, the commutator, again 0. And L squared Lz is 0. Now I ask you to do that for homework. If you find the commutator, you put this value here, this sum here for Lx. Now you can split that sum up into 3 parts, and well, it's probably easier using the XYZ coordinates. So I asked you to do that as well. So the conclusion is that either one of these 3 components, either along the x-axis, y-axis, or z-axis, L hat, angular momentum operator, they are compatible. Each of these three is compatible with the total angular momentum squared operator, L hat squared, okay? Because the commutator is 0. So each of these three is compatible with L squared hat, or L hat squared. Alright? So that means, now remember from a previous lecture, if you have two observables, A and B, and if they're compatible, then they have eigenfunctions in common. They share the same set of eigenfunctions. Okay? So in this case, L hat squared and Lx hat will have the same set of eigenfunctions. Right? These orthonormal eigenfunctions. There's this basis, if you like. Now Lx, Ly and Lz are incompatible. They do not share the same set of eigenfunctions, but Lx shares the same eigenfunctions with Lz, or Ly shares the same eigenfunctions with L squared. Ly shares the same eigenfunctions with L squared, or Lz shares the same eigenfunctions with L squared. But you can't have all three, or even two of them. It's just one. So you need to choose the eigenfunctions of L squared. You're going to have them to be common with the x component, Lx hat, or exclusive or Ly hat or Lz hat. Now convention is you just choose this one. And why is that? Why do you choose the z component? Well, because later, when we come to solve the eigenequation, it's more convenient to use the spherical polar coordinates, r, theta and phi, than it is to use the Cartesian coordinates, x, y, z. And the Lz component, the operator here, is of a particularly simple form. Right? It's just effectively just d phi. So it's very easy. So by choosing this operator, now we only choose one of these three component operator. So let's choose the z component because its operator here has a particularly simple form. The others are more complicated. Ly and Lx, they're more involved. They're more complicated. So let's just choose the Lz form, because when the time comes to actually solve for the eigenfunctions, the fact that the operator here is so simple, that simplifies the solving of the eigenequation. That'll become clearer when we actually do it, but that's the reason for choosing this component to be the one that is compatible with L squared. Right? Okay. Well, that's as far as I've got on board for this session. Alright. Well, what we're going to do now is we now know by convention, so we now know we have two operators, two L squared hat and Lz hat. These two operators commute, right? They commute. And therefore these two operators have a common, the same set of eigenfunctions, right? So we will, and we want to know what those eigenfunctions are, and we want to know what the eigenvalues are. So next session we will write up two eigenequations, one for L squared and the other one, a second eigenequation for Lz, okay, with different eigenvalues of course, but the eigenfunctions will be the same. They'll be the same set. So you'll have the same set of eigenfunctions for both eigenequations, and then we'll launch into solving those eigenequations and learn something about the quantum mechanics of angular momentum. And 2 sessions from now, we will tangent away, we'll steer away from quantum mechanics, and we will get into the details of a particular kind of differential equation which becomes necessary to actually solve one of the 2 eigenequations. But that's 2 sessions away. But just give you a taste of what's coming. Right? So for the next immediate session, we'll write out the 2 eigenequations for L squared and Lz with a common set of eigenfunctions, and we will try to solve them, find what their eigenvalues are and what the eigenfunctions are, which is what solving an eigenequation itself is all about. So